So in this video, we're going to talk about the strengths of acids and bases. All right, and so when we're talking about the strength of an acid and base, really what we're referring to, it's its ability to dissociate. What do we mean by dissociate? Its ability to split into ions. All right, and so a strong acid or base, they dissociate 100%. All right, that means a strong, if it's mixed into water or in any type of aqueous solution or any type of solution, really, those acids or bases will completely dissociate. So what this simply means, so if you have something like HCl, all right, HCl is a strong acid. You put it in water, it's going to break up to H, the hydrogen ion, and the chloride ion. All right, that's exactly what's going to happen. Other strong acids, you have like sulfuric acid. Sulfuric acid is going to break up into hydrogen ion and hydrogen sulfide ion. Okay. Hydroiodic acid, which is another strong acid, is going to break up to hydrogen ion and iodide. All right, the iodide ion. Nitric acid, HNO3. All right, hydrogen ion plus the nitrate ion. Okay. You see, perchloric acid. All right, it's going to break up to the hydrogen ion and the perchlorate ion. Okay, and one more example, hydrobromic acid, which is another strong acid, is just going to break up to hydrogen ion plus the bromide ion. All right, so these are strong acids. All right, and strong acids, when you put them into water or refined solution, they completely dissociate, or they dissociate 100%. And so it's due to this property of wanting to dissociate or dissociate completely, or in other words of dissociation, it's wanting to give up its hydrogen, right? Because these acids, according to Bronsted-Lowry, are proton donors. So it's the ability to donate the proton so easily that makes some of these acids very, very corrosive. All right, and it could cause serious chemical burns, and it can make it really corrosive, especially to to organic tissues and some other substances, right? And it's just because its ability to dissociate so easily. Now, interesting pattern is that these strong acids, all right, so hydrochloric acid, sulfuric acid, hydroiodic acid, nitric acid, perchloric acid, hydrobromic acid, these acids have very, very weak conjugate bases. So here are your conjugate bases, all right, and they are very weak. All right, now what does it mean for us to have a weak acid or weak base, which is an exact opposite of a strong acid, a strong base? So remember, strong acid, strong bases, they dissociate 100%. Or when it comes in the case of an acid, it's wanting to give up its hydrogen very, very easily, right? While we have a weak acid, weak base, right, we're talking about it do not dissociate 100%. Okay, and in the terms of an acid, that means that particular substance won't really release or won't really ionize its hydrogen as easily. Okay, and so And the reason why I said that this right here doesn't makes complete sense, that a very, very strong acid will have very, very weak bases. If you think about wanting hydrogens or losing hydrogen, so a strong acid will want to lose its hydrogen. Okay, so if it wants to lose the hydrogen and it becomes the conjugate base, well, it doesn't really want the hydrogen back because it was trying to lose it to begin with, right? So thus it's a very weak base. So its ability to attract a hydrogen, it's very, very unlikely. All right, so thus a very, very weak base here. All right, sulfuric acid, same thing. HSO4 is a very, very, very weak base. The likelihood of picking up another hydrogen, thus the base, the conjugate base, it's really, really unlikely. All right, and so that's why we say that this is a weak base. Now, when it comes to these strong acids and strong bases, anytime you mix these up with H2O, these reactions hardly ever go into equilibrium. They'll always typically go into complete completion. All right, and so hardly ever the reverse reaction will take place. All right, and so we typically write it this way. All right, where if you have a strong acid, strong base, I mean, it's going to 100% completely dissociate and it won't really go back. All right. And so let me kind of give you another example of this and show you exactly how we typically write a weak acid and weak base chemical reaction. And so, for example, sulfuric acid is a strong acid. All right. And if you were to react it with water, right? And so if this was a liquid and you were to react this with liquid water, what we find that you would get an aqueous solution H3O plus. All right, so remember it's an acid, so it's going to lose its hydrogen. So it's going to make an hydronium and HSO4. All right, and so here we have our acid, right? And the acid is going to become the conjugate base. All right, while the base is going to become the conjugate acid. Now, due to the fact that this here is a strong acid, this is going to be a very, very weak base. All right, but we write it one-sided because H2SO4 is a strong acid. It's going to dissociate. All right, now this right here, it's a is your conjugate base, but because you also have this hydrogen, the second hydrogen, this is a diprotic acid, you know, chances are hydrogen sulfide HSO4 can also give up that hydrogen, right? But this is a what we call a weak acid. All right, because the likelihood of this happening, not to say the likelihood is going to happen, but it won't dissociate at 100%, but like H2SO4 can. All right. And so it can dissociate. So because it can dissociate, this reaction can be at equilibrium. All right. And so if this is your acid, then you're going to also make H3O plus SO4 negative 2. All right. And so now the reaction could actually go both ways, all right, to where the hydrogen sulfide here, hydrogen sulfate, I'm sorry, all right, could dissociate, all right. Some of it will dissociate to become the sulfate ion, and at the same time, this reaction can go in reverse, where the sulfate reacts with the hydronium to make the hydrogen sulfate again. All right, and so you have this a constant change of this reaction always taking place, and it's going to be at equilibrium. All right, and so anytime we have a weak acid and a weak base, and is reacting with something here like water, it will exist in equilibrium because some of it will dissociate, some of it won't, and then as some of it are dissociating, then at the same time it will reassociate, or the hydrogen will reattach to the conjugate base here to form the weak acid again. All right. So now, why is that the case? Well, because this is a weak acid, that means that it may not always want to give up the hydrogen. So there is some affinity for hydrogen, all right? And because there is some affinity for hydrogen, this base here, all right, will actually go this opposite direction and basically accept the hydrogen from this hydronium ion, and so that way then it will return to HSO4 again. So this is the reason why the reverse can happen, because the weak acid has a stronger weak base, or a stronger conjugate base, and if it has a stronger conjugate base, the base will be able to accept the hydrogen, and if it's able to accept the hydrogen back, well, then the reaction could go in reverse.